All right, welcome everybody to the AFWERX Fusion panel discussion, the process of reverse engineering. I'm happy to have four wonderful panelists here. I'm going to let them introduce themselves, and then we're going to go through a couple of predetermined questions just to get some conversation going, and we'd love to hear some questions from you. So if you look down and use that Q&A button at the bottom of your Zoom window to make sure that you're asking the questions, then when there's some time in the panel, I will make sure that that question is asked to the group. Okay, so Brian, why don't you go first, and we'll do a quick introduction, then we can go on with our questions.
I'm Brian Stitt with the University of Dayton Research Institute.
Brian Brown with MSC Software, a Hexagon company.
Perfect.
Charlie McElroy with Stitt Diagnostics.
And Ryan Myers with Hexagon, primarily on the metrology side.
Okay, wonderful. And at the end, I will make sure that I show their emails again here at the end of the panel. I want them all to have equal billing, so they're all in the view for you. So our first question is a sort of a two-parter. How can digital data become useful over the life cycle of a part? And then how can the digital twin of the reverse engineered part be used to predict failures? So who would like to start on that this morning, or this afternoon, excuse me? Don't everyone jump in.
Well, I think Brian and I, both Brians here, have some thoughts on this one. So I think, you know, a couple parts on the digital twin and digital thread, you know, modeling simulation, starting all the way from design, pulling it through modeling simulation into the production side, which includes the process steps and scanning metrology, and back potentially at the point of ingesting that scanned data, whether it's through eddy current or CT scans, and bring that back into modeling simulation so you can predict the life cycle of that part. Later, we're going to talk about effects of defects, but in short, that process from design all the way through manufacturing to include the analysis is a critically important element to 3D printing, and be able to understand all the subtleties and variabilities, as it's very complex. And so that the value of it, in other terms, is a digital currency. And so I think, in short, it's being able to understand it sufficiently well enough that you can then optimize the designs and optimize processes, so that the ultimate goal is that when you hit print, you're hitting print and getting it right the first time.
Yeah, I think that's a great explanation. I think product lifecycle management is just more and more critical as we go forward. It starts from your digital input, so the ingestion of that digital data, all the way through to when a part is traced through its life cycle out in the field. Understanding how you can use this data to, as we said, predict failures, you know, driving scheduled maintenance versus unscheduled maintenance. So, you know, anticipated versus unanticipated is a big way that we can drive improvement in readiness. And as well, Brian mentioned that a lot of these emerging technologies continue to require digital data as their input. So whether it's a historical manufacturing process, whether it's CNC or additive, all of those are requiring more and more digital data, leading to the modeling and then throughout the life cycle of the part.
Now, I'll buttress those comments too, and as the data becomes more rich and the processes become more understandable and the variabilities also more understandable, it is then we can buttress it with artificial intelligence and machine learning that then adds an extra layer of confidence in our parts performance and our manufacturing processes. So again, it's going back to Brian's point of, with regards to specifically from a DoD perspective, operational readiness levels for that system or the part can be improved significantly through good engineering, which is then reinforced by good data. So garbage in is garbage out.
Yep. And this is going to lead to some of the follow-on questions where we talk about how the data can be used and so on. So I believe that getting into the modeling side and how we validate parts is all going to drive this digital thread and the digital twins associated with these parts and hardware.
Yeah. All right, so our next question is, what is the best way to establish or find the qualification requirements for a legacy part? Now should one move forward if that data is not available? So who wants to take that?
I'll start with it, and then probably some of the other folks can add on, but be able to capture the data out of a reality one of two ways, or actually one of three ways. Probably if you have digital data already, which is rarely the case on Air Force sustainment parts, most likely what's going to happen is that what you would consider a golden part be scanned, brought into the digital world, and then you can begin your digital optimization for additive based on the digital data that you grabbed off the scan part. And yet another way would be able to create a 3D model from 2D CAD.
I'd like to follow up with that as well. We want to get away as we look at part qualifications for these emerging technologies and what's out there from a legacy standpoint. As you said, a lot of times the data is not there. But I think as an industry, we need to get away from point design and point qualification for every single part number and try to get to a point where we're actually doing categories of parts or families of parts and leveraging all the hard work that's done to do those initial validations and then being able to progress that further as a family. So it can be anything from metallic parts to cast parts or whatever it might be. It allows us to then go through the process more once for the family, and then anything that comes up that's critical for an individual part, we can test or evaluate that. But from a cost standpoint, I also think modeling has got to be a big part for trying to make sure we understand qualification requirements, because you don't necessarily always want to do physical qualification. As Ryan was saying, getting into the modeling side and having the digital part is a big driver, and being able to do comparisons within the modeling and doing sensitivity studies is a big way that we can get an understanding of the equivalency of the parts for qualification.
I think as a small add to this conversation too, as it relates to legacy parts and using potentially modeling simulation to facilitate the qualification of those parts, and absent data being load path generation that you may or may not have from the legacy systems themselves, there are other ways of doing that through modeling simulation where the models themselves can generate loads. And if you generate enough use cases, as example, like design of experiments, and do a battery of analyses, you can then create a design space and sufficiently define an operating environment. And within that operating environment, you even may ask subsequent questions on, do we have the liberty to do something creative for that part? Example, create a lattice type structure and do topology, topography optimization on that part and explore that design space even further. So even absent of having the legacy data, there's still ways in which we can create a design space and manufacturing space that is definition for that part and component that can be pushed forward through the life cycle of the manufacturing process and the life cycle of that part in use.
Yeah, that's absolutely true. And it ties back, as I kind of gave a precursor earlier on, that all this was going to tie into the digital side of this. That's absolutely true. And being able to pull in some of the system level analyses ensures that as we go through the design process for an additive part or other emerging technology, that we don't drive a failure mode somewhere else in a system. So not only does it rely on what we want to do for that part, but it goes back to that system level analysis too. So fully support what Brian was speaking there as far as design space.
All right, so I have a third question. I think, Charlie, this is for you. What are some of the ways that AM manufacturers can decrease the presence of defects in their builds?
Well, as my illustrious colleagues have been discussing, the digital twins are extremely important. One of the things we're working on, and I'm sure they are as well, is looking at a multimodal fashion of trying to draw in the various digital information and then using machine learning to optimize the process. So one of the things we're very excited about is looking at how can we use causal analysis with the various features that we're getting for the digital twin to drive the quality improvement. And we think that that's going to be a major step forward for the industry as a whole. And I think we're very excited at being at the ground level starting right now.
Great. Anyone else want to add to that?
Yeah, I think as a follow-on, everything you said is absolutely true. We want to be also looking at everything from build chamber gas flow to the incoming materials from material vendors. All of that is going to drive the variability that goes into additive and the AM manufacturers and what type of parts they can get out of their process. So I think we need to continue looking at all the sensor capability, but also go back and look at the powder capability and the build chamber gas flow characteristics to ensure we're reducing the variables.
Okay. I want to remind our audience that we haven't gotten any questions yet, but I know that there's got to be some really interesting ones brewing out there. So don't be scared. Type your question in the little Q&A box at the bottom of their Zoom window, and we'll make sure we get to it. All right. So next question, do you think that the ability to add material composition sensing would be a good addition to 3D scanners?
Yeah, this is Ryan. Absolutely. We're trying to lean forward and anticipate combining technologies in other areas that would not only just give you a 3D point cloud of a system, but also looking inside the part as well while you're doing your 3D scan to kind of give you material composition and you know, for both capturing initial data to bring it into the digital thread, as well as for inspection and after, looking at you know, various technologies such as terahertz imaging. CT is obviously one, but being able to do that on a portable basis is sort of a challenge right now, but we're kind of leaning into that direction, and other NDT modalities such as phased array ultrasonic and things like that we're looking at to kind of capture those types of elements in a scan.
And from a reverse engineering standpoint, thinking of the technology, a lot of people think of reverse engineering as more the dimensional characteristics or the GD&T of the part. And a lot of organizations don't necessarily think of the material characteristics and the details behind the materials. But I think material type and composition is almost a bigger characteristic that helps drive the end performance of the part. So being able to capture that during the scanning capability and reduce the time and cost to get parts out into the field is definitely a win.
So I'll comment on the same question. I think at the basic level the question is in situ monitoring and potentially a value. And so I do agree with my colleagues, in situ monitoring is a critically important. I think there are a lot of challenges in that domain. Example, if you use metal-based additive, where the layers, you know, potentially as the fifth pass goes across, the first layer or 4 layers below it may have potentially been impacted positively or negatively by that 5th layer. So while you're doing in situ monitoring, you may identify a defect. 5 layers later, that defect may be fixed. So then it becomes really comprehensive in regards to in situ monitoring. What are the effects of those defects? Are those defects going to self-correct or not? And it's a very complex dynamic system, manufacturing processes for us to say definitively how and where the in situ monitoring is going to really take significant hold in helping us improve, optimize, and qualify the parts and the processes for manufacturing.
Yeah, that's a direct tie back to what AM manufacturers can do to decrease the presence of defects, but it also is a direct correlation to, you know, what are next steps in additive research.
Yeah, so we have about 5 minutes left, so I want to make sure that, yeah, that's my next question is, what are really some of the most important next steps that need to happen and for additive manufacturing? Charlie, you're going to try, there you go.
Right. I think part of the things that I'm so very excited about, as Brian and Brian were just mentioning, is the amount of data, and it is a hyper complex system. There are multiple interdependencies, but I think one of the most exciting things is how can we use leverage some of the machine learning tools that we have to bring that under control. And I think we're beginning to see that, for instance, a number of projects where they're able to reduce to a defect or near defect-free part. And I think that is going to be, once that happens, that's a threshold that once we're able to do that routinely, I think that's going to open up the entire industry And I think the Air Force is going to be particularly excited about it, because then they'll be able to employ this type of manufacturing process in a wider range of spectrum they currently do for their airplanes. So I think that that's one of the areas I think we're most excited about seeing that progress in the industry.
Yeah, and I think that's a broad question, you know, because I think the level of research that's needed is kind of dependent on the type of AM, whether it's metals, polymers, FDM, powder bed. You know, I think each one of those drives a different level of what needs to be done in the next steps. But I think they all go back to what Charles was saying, is that you know, we got to get to better process capabilities. We got to be able to use the AI and machine learning to help us do that, and basically leverage the appropriate technologies to go do this research so that we can get to better process capabilities to push this to the mainstream.
Yeah. All right. Well, let's see. I think I lost Tad. There was a question: how robust is part simulation within the design community based on the benefits of AM? I think Tad, I don't know where he went. Oh, there he is. Tad,
Yeah,
all right, do you want to clarify? I know Brian asked you to clarify some. Do you want to add on to that?
So my question, and I am not a simulation guy, but I know a lot of people that are, but it seems like they're few and far between. And I guess my question is, when we do simulations today, we do a lot of simulations based on traditional manufacturing elements or entities. How do you see design, component engineering, simulation, part simulations, not build simulations, but part simulations, given the unlocking of capabilities that AM can provide?
So I'll take this first stab at it. So Tad, thank you for the question. Certainly thank you for the follow-up clarification. And you're right, the additive manufacturing value can be significant as a contrast to traditional manufacturing, and we won't have to get into that here. But as it relates to the process design and analysis, in our view, it's a complementary organizational capability that should be tied to the manufacturing processes. So the manufacturing boundary conditions of additive manufacturing need to be brought into the design community as well. So examples where you have generative or topology optimization tools that are leveraging the load paths to remove material that's not necessary for that component or that part. And then the boundary conditions are not only where that part is going to be affixed within the system, but it's also the boundary conditions of the manufacturing. Just because you can design it doesn't mean you should manufacture it. Example would be the support structure that would go within that lattice type structure. It may be hard to machine it out. So understanding what the restrictions or boundary conditions are in manufacturing and be able to bring that in and buttress it within design and analysis, and using analysis to not only optimize the parts, design, and components, but also take in consideration the life cycle of that part in use. And so there is and then the other parts too do include where modeling simulation can predict the manufacturing process and the effects of the manufacturing process to deformation of that part through the process. And then you can use design simulation to then pre-compensate or compensate for those deformations, so that it may, when it hits print, it may actually show up to the printer with a compensated geometry that when it is finally done with the manufacturing process, it's deformed as intended for use. So I'll pause and turn the floor over to Brian, and then certainly Tad, if that doesn't address your questions, we can delve further.
Yeah, I think, I know we're out of time here, I think, but I think that the tools are quite robust, and the use of the tools is becoming more and more widespread. Again, it's going to be the results that you get out of these tools are going to be driven by what types of properties you place into the tool. So having good materials data for the types of prints that you're doing is a big driver, so that you don't have to debit properties or anything like that. You can use real design allowables within your tools, and you can get more realistic data out of the tools. So it's a big driver is the input to the tools as well.
Thank you.
All right. Any last minute thoughts? We have maybe a couple more minutes left before we head back over to the main AFWERX Fusion live stream on the website.
You know, if we have just a minute, one thing we could talk here is as we go through these additive type processes and emerging technologies, the foundation of them is still quite critical, and making sure that we have education within the current workforce, so workforce development and education for future engineers and designers and so on through universities and colleges is quite critical as well. So getting that mindset change for how the designs are going to look different and perform the same or better is a big deal, and it's a paradigm shift, but it's a big part of the foundation to continue to grow.
All right, well, I am highlighting their contact information for everyone. If you'd like to heard something interesting and you want to follow up with them, you can reach them via these email addresses. And I certainly thank you all so much for your time and your energy and your effort and your curiosity today. So everything is starting back up on the main website, AFWERXfusion.com. They'll start live streaming here shortly. Everyone have a wonderful day. Thank you so much.
Thank you. It was a pleasure.
Appreciate it.